Now in this video, we'll explore the rationale behind second derivative test. Now in order to understand the rationale behind second derivative test for multiple variables, we'll try and understand the logic behind second derivative test for functions in two variables. Suppose we have a function y equals fx and f dash x is 0 at say x equal to a. So x equal to a is a critical point in this case. Now from Taylor's series we know that we can write fx as fa plus f dash a into x minus a, f double dash a into x minus a square upon factorial 2 plus f triple dash a x minus a cube upon factorial 3, and this series will continue. Now we can write this as fx minus fa. Now a is a critical point, and if a is a critical point, then at a f dash x is 0. So this term will be simply 0. So we'll get f double dash a into x minus a square upon factorial 2. Now when we say point of local maxima or local minima, it simply means that we are looking at the value in the neighborhood of a. So that means this x, it is a plus or minus h, where h is nearly 0. So it simply means that this x minus a, it's a very small quantity, and if it is a very small quantity, then as the power increases, the value decreases. So we can ignore higher powers of x minus a. So we get this result, which is fx minus fa, it is equal to f double dash a upon factorial 2 x minus a square. Now if f double dash a is greater than 0, in that case we can write fx minus fa is greater than 0, which simply means that fa is less than fx for all the points x in the neighborhood of this point a. So it simply means that this x equal to a is a point of local minima. So if second derivative is positive, it simply means that this point is a point of local minima. And if second derivative is negative, then we'll get f double dash a less than 0, which means fx minus fa is less than 0. That is, fx is less than fa. So for all the points in the neighborhood of a, the value of this function is less than the value at this point a. So it means that this x equal to a, it is a point of local maxima. And if f double dash a is 0, then in that case we'll have to look for sign of f triple dash a. So that means now this second derivative test is inconclusive. Now we'll try and figure out the rationale behind second derivative test for multivariable functions. So suppose we have a function, say z equals fxy, and we have a critical point at ab. Now again we'll use Taylor's expansion for two variables. So we can write fxy equals fab plus fxab into x minus a plus fyab into y minus b plus 1 by 2 fxx x minus a square plus 1 by 2 fyy y minus b square plus fxy x minus a y minus b, and this series will continue. Now we know that at critical point a and b, first derivative fx, it is 0, and fy 0. So both these partial derivatives, they are 0. So we can write this as fxy minus fab, and it'll be equal to 1 by 2. Now we have taken fxx as a, so it'll be a into x minus a square plus 1 by 2 fyy is b, so it'll be b y minus b square and plus c x minus a into y minus b plus all other terms. Now again, we are looking for points of local maxima and local minima. That is, we are looking for the points in the neighborhood of a, b. We can ignore higher powers of x minus a and y minus b. So we can write fx minus y minus fab, it is nearly 1 by 2, and then a, x minus a square, b, y minus b square plus 2c x minus a into y minus b. Now here what we'll also do is we'll take y minus b square common from this bracket. So we'll write 1 by 2 y minus b square. So we'll get a x minus a upon y minus b square plus 2c x minus a upon y minus b and plus b, which is a quadratic equation in x minus a upon y minus b. So we'll take x minus a upon y minus b as some variable, say t. We can simply write f xy minus f ab as 1 by 2 y minus b square at square plus 2ct and plus b. Now this expression, it is already positive, so everything will depend on sign of this quadratic expression. Now we know that if a is greater than 0 and if d is less than 0, then this quadratic expression at square plus 2ct plus b, it is always positive for all t belongs to R. So it simply means that in that case fxy minus fab, it will be greater than 0 in the entire neighborhood of ab. So we'll get this condition fxy is greater than fab. So for all the points in the neighborhood of ab, the value at ab is the lowest. So from here we can say this fab, it is a point of local minima. Now what is the condition? We need to find d. Now d for this function is 4c square minus 4ab. So condition here will be a is greater than 0 and d, which is 4c square minus 4ab, it is less than 0. So from here we'll get ab minus c square, which is our h, and h is greater than 0. So this function, it will have a point of local minima when h is greater than 0 and when a is greater than 0. Now if a is less than 0 and d is less than 0, then this quadratic expression at square plus 2ct plus b, it is less than 0 for all t belongs to R. So it simply means that fxy minus fab will always be less than 0. So we can write fxy is less than fab, which simply means that this fab, it is a point of local maxima. So we'll have a point of local maxima when a is less than 0 and d is less than 0. And d again is c square minus ab is less than 0, which means h, which is ab minus c square, is greater than 0. So if we have h greater than 0 and a less than 0, then it will be a point of local maxima. Now if d is greater than 0, then this quadratic expression, whether opening upwards or downwards, somewhere it will have positive value and somewhere it will have negative value. So in that case, this point, it will have a value which is greater than value at some points, and it will have a value which is less than value at some other points. Then in that case, it will simply be a saddle point. And if d is equal to 0, then again test fails. So that is the logic behind second derivative test for multivariable functions.